In this video, I will show you how to evaluate some complex limits using L'Hopital's rule if necessary, and sometimes we will need to use logarithms. For problem number 50, I think we will have to use logarithms. Whenever I notice that we have a variable in the exponent, usually we need logarithms to fix this. We will end up using a property of logarithms. Here's an example. If I have the natural log of 5 to the x power, I can take the exponent and put it in the front. So x times the natural log of 5 would be equivalent. So if we can somehow introduce logarithms into this process, we can get the variable out of the exponent where it is sort of messing up all of the rules that we use. So how do I get logarithms into this limit process? We're going to need a couple of tricks. The first one is to let y equal the function that we are trying to find the limit of. Now, in that way, we can rewrite the limit as x approaches infinity of y. So we just have to find the limit of y. Next, take this equation and write it off to the side where we can play around with it a little bit. This is where we will get logarithms involved, so we can move the x to the front eventually. Specifically, let's take the natural log of both sides of this equation. So now we have this. When you take the natural log of something that has an exponent, as I reminded you earlier, you can take the exponent and move it to the front. So now we have this. But let's not forget that we really need to find the limit as x approaches infinity of y. We can start by finding the limit as x approaches infinity of natural log y. In fact, let's take the limit of both sides of this equation. So far we have this. I would like to rewrite this expression as a fraction so we can use L'Hopital's rule to help us evaluate the limit on the right-hand side. The easiest thing to do would be to drop the x down to the denominator and make it x to the -1 power. So now we have this. In order to use L'Hopital's rule, we need to find out if the numerator and the denominator both approach either infinity or they can both approach 0. If either of those is true, we can use L'Hopital's rule. In the numerator, focus on the 1 over x part. As x approaches infinity, x is getting bigger and bigger, so the value of this fraction is getting closer and closer to 0. So we have natural log of 1 plus 0. This is really just the natural log of 1, which is 0. So the numerator is approaching 0. X to the -1 power is the same as 1 over x. As x approaches infinity, the denominator is getting larger and larger, so the overall value of the fraction is getting smaller and smaller and approaching 0. So the numerator and denominator are indeed both approaching 0. You don't have to show all of that work. You can do that in your head, but you do have to indicate that the numerator is approaching 0 with an arrow, and you must indicate that the denominator is also approaching 0 with an arrow. This tiny part here is part of the justification for using L'Hopital's rule. So you cannot skip this part. You must show this, or else you're not allowed to use L'Hopital's rule. I'm going to have to scroll to the right in a moment, but I wanted to show you that so far I just copied down the left side of the equation. So I have the limit as x approaches infinity of natural log y equals. And I'm about to perform L'Hopital's rule on the right-hand side. So what is L'Hopital's rule anyway? I keep saying it over and over again. L'Hopital's rule says that if the numerator and denominator are both approaching 0, or if they are both approaching infinity, we are allowed to take the derivative of the numerator and the derivative of the denominator, and that will not change the limit. So I am about to take the derivative of the numerator right now. We know that if I take the derivative of natural log x, that is 1 over x. That's a rule that we have memorized. So I see this natural log here. If I take the derivative of this natural log, I'm going to have 1 over something, just like I have 1 over x. But because I have this entire expression, instead of just 1 over x, I'm going to have 1 over 1 plus 1 over x, all right? Everything on the inside. Because I have a whole function inside of the natural log, I have to use the chain rule, and I have to go ahead and multiply by the derivative of what's inside of here. I have to multiply by the derivative of this. The derivative of a constant is 0, so I'm going to ignore that. But how do I take the derivative of this again? 1 over x is equal to x to the negative 1 power. If I take the derivative of x to the negative 1 power, I can just do the power rule, put that negative 1 in the front, and then reduce the power by 1, so I get negative 2. So that's what's going to happen here, and I will multiply by negative x to the negative 2 power. I can simplify this later, but I have taken the derivative of the numerator. Now I will take the derivative of the denominator. Well, I already mentioned that right here. The derivative of x to the negative 1 power is negative x to the negative 2 power. So this will be negative x to the negative 2 power. But this is pretty neat because I have the exact same expression in the numerator and the denominator. So these will just cancel each other out. So now we just have this, which came from right here. It's the only part that's left. Let's analyze the limit as x approaches infinity. So as this little x right here gets bigger and bigger, the value of this fraction gets smaller and smaller. The value of the fraction is approaching 0. So that's just going to leave behind 1 over 1. So the limit is 1. We have now found the limit as x approaches infinity of natural log y. But we really wanted the limit of just y by itself. So here's another trick that we can use. We can exponentiate both sides of this equation. Even though there's a limit here, this still is valid. So if I could put a base e on both sides, the base e and the natural log cancel each other out, and that just leaves y. So we end up with the limit as x approaches infinity of y is equal to e to the first power, which is simply e. So this is the answer to the question. Notice that we have the limit as x approaches infinity of y is e. Now look back, and that's exactly what we were trying to find, the limit as x approaches infinity of y. And we found it. And remember, this y really represents the entire initial expression, the initial function of which we were trying to find the limit. So we've done it. For number 52, I'm noticing that we once again have this variable in the exponent. To fix this, we will need to introduce natural logs into the limit. But first, let's let y equal all of this stuff right here. So y will equal 1 plus x to the 1 over x power. That means the original problem can be thought of as the limit as x approaches infinity of y. That's all. Doesn't that make it seem easier? Let's take this y equals equation and write it off to the side where we can play around with it. So y equals 1 plus x to the 1 over x power. Now let's take the natural log of both sides of the equation. So I have natural log y is equal to natural log of 1 plus x to the 1 over x power. The point of doing this is so I can take this exponent and bring it to the front, because that is a property of logarithms. So I have natural log y is equal to 1 over x times the natural log of 1 plus x. Let's get limits back into the mix by taking the limit of both sides of this equation. So we have this. I would love to use L'Hopital's rule on this side of the equation, but first I need to rewrite this as a fraction. I already have the 1 over x, so all I really need to do is take this and stick it in the numerator. Kabam. So now I have this. We can only use L'Hopital's rule if the numerator is approaching infinity and the denominator is approaching infinity, or 0 over 0. As x approaches infinity, the function inside the natural log is just getting bigger and bigger and bigger. So the numerator is approaching infinity. Of course, x itself is approaching infinity because that's what it says right here. So the denominator is also approaching infinity. Since we have this infinity over infinity, we can use L'Hopital's rule. Once again, please let me emphasize that this small little step is 100% necessary. This is an easy way to justify using L'Hopital's rule, but you must show with an arrow from the numerator and an arrow from the denominator that each is approaching infinity. According to L'Hopital's rule, we can take the derivative of the numerator and the derivative of the denominator without changing the value of the limit. This only works when you're approaching infinity over infinity or 0 over 0. But what is the derivative of natural log? We reviewed this on the previous problem, but I'll just say it again. If I have the derivative of natural log x, that is 1 over x. So the derivative of this natural log will be 1 over something, but it's not just x, it's 1 plus x. So I'm going to put 1 plus x right here. Because we have this function inside of a function, I need to multiply by the derivative of this inner function, but the derivative of 1 is 0, and the derivative of x is 1. So I don't really need to show multiplication by 1, so I'm just going to erase that. Furthermore, I need to take the derivative of the denominator. The derivative of x is 1. Ignoring the 1 in the denominator, we have this. Let us analyze the limit again. So as x approaches infinity, this denominator is getting bigger and bigger and bigger, while the numerator remains a constant. So the overall value of the fraction is getting smaller and smaller and smaller and approaching 0. So the limit is 0. By the way, we did not really need to use L'Hopital's rule on this problem. Back in Unit 1, I taught you this acronym FEPL, which reminds us that as x approaches infinity, some expressions grow faster than others. Specifically, factorials grow faster than exponentials, which grow faster than polynomials, which grow faster than logarithmics. So in this case, in the numerator, we have a logarithmic expression. I'm going to put an L next to that. in the denominator, this is a teeny tiny polynomial. So we have a polynomial expression in the denominator. So polynomial expressions grow faster than logarithmic expressions. So while the numerator is approaching infinity, it is approaching infinity slower than the denominator. The denominator is approaching infinity faster. So we learned that if the denominator is growing faster than the numerator, then the denominator is getting bigger and bigger and bigger compared to the numerator. And if the denominator is getting bigger and bigger and bigger, then the overall value of the fraction is getting smaller and smaller and smaller. So we automatically know that the limit is 0 without doing L'Hopital's rule. Anyway, we really need to find the limit as x approaches infinity of y, not natural log y. So the trick that we can use to get y by itself is we can exponentiate both sides of this equation. Even though there's a limit expression here, it still is valid. Base e and natural log are inverse functions, so they cancel each other out, and that leaves you with just y. And then we have e to the 0 power, but a constant raised to the 0 power is 1. So the limit as x approaches infinity of y is 1. And this is the final answer. Because remember, back at the beginning, we let y represent the entire function. So by finding the limit as x approaches infinity of y, which we found is equal to 1, we were finding the limit of the original expression. Number 54, I see a variable in the exponent again. So we will probably need the natural log once again. So let's start by letting y equal the entire function. So we will let y equal 3 times x minus 4 all raised to the x minus 4 power. So we can think of the original problem as the limit as x approaches 4 from the right of y. So here I've written the equation off to the side so I can take the natural log of both sides. The point of taking the natural log of both sides is so that I can use the property of logarithms that allows me to take the exponent and put it in the front. So now I have this. Let's get limits back into the mix by taking the limit of both sides of this equation. So now we have this. Hey, maybe we can just do direct substitution. If I let x equal 4, I have I have 4 minus 4, so that would be 0. And then 4 minus 4 again, so that's 0. Natural log of 0 is undefined, so no good. Instead, let's shoot for L'Hopital's rule by taking this expression and dropping it down to the denominator as x minus 4 to the negative 1 power. So now we have this. In order to use L'Hopital's rule, we have to determine that the numerator and the denominator are both approaching 0, or they have to both be approaching infinity. To understand what's happening to the numerator as x approaches 4 from the right, first remember what the function natural log x looks like, and remember what happens to this function as x approaches 0. As x approaches 0, the value of this function falls and falls and falls and approaches negative infinity. So I need to convince you that that is what is happening here. As x gets closer and closer to 4, this expression inside of the parentheses gets closer and closer to 4 minus 4. It gets closer and closer to 0. So in other words, this entire expression gets closer and closer to 0. In other words, natural log x, all right, this x, the stuff inside of here, is approaching 0. Because all of this is approaching 0, then the natural log expression will be approaching negative infinity. All right, just like we show here. What about the denominator? X minus 4 to the negative 1 power is the same as 1 over x minus 4. So think about what's happening to the value of this fraction as x approaches 4 from the right. In other words, imagine that x is 4.1, and then 4.01, and then 4.001. So we're getting closer and closer to 4. When you subtract 4 from each of those numbers that I just said, you'd see that if this was 4.1, you subtract 4, and this would be 0.1. Let's get a little closer. Let's say this is 4.01. You subtract 4, and then you've got 1 over 0.01. Let's say this was 4.001. Subtract 4, and you've got 1 over 0.001. So this would continue as we get closer and closer to 4. From the right, the denominator will be getting smaller and smaller and smaller, like 0.1, 0.01, 0.001, 0.00000001. If you take 1 and you divide it by a teeny tiny number, it gets bigger and bigger and bigger and bigger. So this is approaching infinity. This counts as infinity over infinity, so we can go ahead and use L'Hopital's rule. Please don't forget to show this little step, which justifies using L'Hopital's rule. Since we are approaching infinity over infinity, L'Hopital's rule says I can take the derivative of the numerator and the derivative of the denominator without changing the limit. So that's what I'm going to do. We know that the derivative of natural log is 1 over x. But because this is not simply x, I'm not going to have 1 over x. I'm going to have 1 over all of this. So 1 over 3 times x minus 4. However, because we have this function inside of a function, we have to do the chain rule and multiply by the derivative of all of this. When you take the derivative of something and there's a constant in the front, you can just leave the constant alone and move on to the next part. But the derivative of x minus 4 is just 1, so I really just have this 3. On the next step, I'm actually going to take this 3 and put it up into the numerator. But for now, let's go ahead and talk about the denominator. Let's use the chain rule. So I'm taking the derivative of x minus 4 to the negative 1 power. So I'm going to move that negative 1 to the front. So I have negative x minus 4 to the negative 2 power. And normally I would then use the chain rule and take the derivative of the stuff inside, but the derivative of x minus 4 is just 1. So I don't need to write that down. So this is the derivative of the denominator. So I'm going to go ahead and put that here. Negative x minus 4 to the negative 2 power. So on the next step, I'm going to do a couple of things. I'm going to put the 3 in the numerator. Maybe I'll just do that. Actually, these 3's just cancel each other out. So those 3's are gone. And then we have the 1 over x minus 4, which is right here. And that leaves the denominator, which is negative x minus 4 to the negative 2 power. But I can rewrite that in this way. Okay, that negative 2 power, I can sort of drop it down to the denominator. But we know that when you divide a fraction by another fraction, you multiply by the reciprocal. In middle school, they might have said keep, change, flip, but this is AP calculus. So we're going to say we multiply by the reciprocal. So I have my 1 over x minus 4 that you see right here, but I multiply by the reciprocal and I get negative x minus 4 squared over 1. Hopefully you can see that we have x minus 4 in the denominator, and then we have 2 factors of x minus 4 in the numerator. So the x minus 4 in the denominator is going to cancel out 1 of the x minus 4's in the numerator, and that will leave x minus 4. Don't forget the negative sign though. So that leaves us with this. And now we can do direct substitution. Letting x become 4, we have negative 4 minus 4, which of course is 0, which is fine. But remember, we don't really want the limit of natural log y. We want the limit of just y by itself. So we can use that trick where we exponentiate both sides of this equation. And that gives us the limit as x approaches 4 from the right of y, because the base e and the natural log cancel each other out. And then e to the 0 power is 1. So this is the answer. Remember, way back at the beginning, we were simply looking for the limit as x approaches 4 from the right of y, and now that turns out to be 1. This matches the original problem because y is the entire original function. So finding the limit of y is finding the limit of the original function. For these last few problems, I want to remind you that we don't always need to use L'Hopital's rule. Very often, we can just use the skills that we learned back in Unit 1 when we first learned how to evaluate a limit. On number 58, right away I noticed that we have a common denominator. So let's go ahead and combine these two fractions into one fraction. Usually when we are finding a limit and we see a square root in the numerator or the denominator, we try rationalizing by multiplying by the conjugate. So let's try that now and see what happens. So I'm going to multiply by the conjugate, which would be 1 plus radical x minus 1. And I have to do the same thing in the denominator. In the denominator, I just have x squared minus 4 times 1 plus radical x minus 1. In the numerator, the whole point of multiplying by the conjugate is that you're going to get a squared minus b squared, where this is a and this is b. So a squared will be 1. Be very careful here. B squared makes the radical go away, but I have to put the x minus 1 in parentheses. So this is a squared minus b squared. I need to distribute this negative sign, and I don't want to recopy the whole thing just for this one step. So this minus 1 will become a plus 1 when I take away the parentheses. Now let's combine like terms. We have 1 plus 1, so that'll be 2. This numerator is backwards. I don't like that. I want to flip this around, and when I do, I will have to take out a negative sign. So 2 minus x is the same thing as negative x minus 2. On my next step, I'm going to factor the x squared minus 4. This is the difference of two squares, and I have a feeling we will be able to cancel out the x minus 2. Notice that we have a common factor of x minus 2 in the numerator and the denominator. So let's cancel those out. At this point, direct substitution should work. Let's go ahead and let x equal 2 and see what we get. But then 2 plus 2 is 4, and 2 minus 1 is 1. The square root of 1 is just 1. So this is 1 plus 1, which is 2. 2 times 4 is 8. So the final answer is negative 1 over 8. And that's the limit. We could have left our answer like this if we wanted to. But what if there is a multiple choice question? So make sure you do have the ability to simplify if you need to. Number 60, we can make like denominators by multiplying by x in the numerator and the denominator. So let's go ahead and combine these. So we have the limit as x approaches 0 from the right of 10x minus 3 over x squared. We can just do direct substitution on this problem. So we have the limit as x approaches 0 from the right. And let's let x equal 0. So we have 10 times 0 minus 3 over 0 squared. So that's, well, once I make the substitution, I don't write the limit anymore. I should just put an equal sign. Well, this is just 0 minus 3. So in the numerator, I have negative 3. In the denominator, I have 0. And this is undefined. So as far as the limit, we say does not exist. Direct substitution will work again on number 80. Let's let x equal 0 and see what happens. We get e to the 2 times 0 minus 1 over e to the 0. Well, e to the 2 times 0 is really just e to the 0 power, and a constant to the 0 power is 1. So this is 1 minus 1, and e to the 0 power is 1. So this is 0 over 1, which is just 0. So that's the limit. Number 82 is not an indeterminate form. Focus on the 1 over x part. We know that as x approaches infinity, 1 over x approaches 0, because as the denominator gets bigger and bigger and bigger, the value of the fraction gets closer and closer to 0. So this yellow is approaching 0. So the original limit would be the same as the limit as x approaches infinity of x times cosine 0. But we know that the cosine of 0 is 1. Here's the unit circle. Here's 0. This is 1 comma 0. The cosine is the x value. Cosine of 0 is 1. That means the limit is equivalent to the limit as x approaches infinity of x times 1, which is just x. So of course, as x approaches infinity, well, x approaches infinity. So this limit does not exist. We could say that the limit approaches infinity, but I prefer to say dne.